live.
Welcome to Slooh, the cosmic classroom where educators bring live astronomy into their classrooms to inspire and engage their students in the study of space, astronomy, and now Earth sciences. Students and members use Slooh's live telescopes in the Canary Islands, Chile, and our new Australian observatories to capture images of celestial objects that they use in our unique curriculum-aligned Quest learning activities. Now then, we've probably got a screen share coming up. We were hoping to bring live images from one of the huge telescopes located at our observatory at the Institute of Astrophysics of the Canary Islands. But if we have a look at our all-sky camera in the Canary Islands, we'll see that we've got a few clouds tonight, but we've still got plenty of images of the Blaze Star to share with you. Now, I'm Paul Cox, your host this evening, and together with our expert guests, we'll be learning about a peculiar star system that students using Slooh have been monitoring every night since March. We'll be sharing some of their images later. They've already captured hundreds of images, but why, there's the all-sky camera. My goodness, you cannot see a single star, can you? That's bad news, but students have already been using the Slooh telescopes to capture these hundreds, probably thousands by now, of the Blaze Star. But why? Why have they been doing that? Well, this system is known scientifically as T Coronae Borealis, but it's commonly called the Blaze Star. It's rare because it explodes once every 80 years or so. The star system is 3,000 light years from Earth and consists of a dead white dwarf star and an aging red giant star. We'll learn more about it with our expert guest, Dr. John Bovair, and our special guest, Stanford University student and longtime Slooh member, Michelle Park, who wrote and published a scientific paper on variable stars using Slooh. It is an amazing story, and you do not want to miss it later. Now, many nova have been discovered. That's when a star explodes, but few of them are known to be what's called a recurrent nova, like the Blaze Star. So this is a once in a lifetime. I really cannot emphasize this too much. So certainly for me, maybe not for some of you youngsters, but for me, this is a once in a lifetime opportunity for students and Slooh members to witness and capture this rare cosmic event using Slooh's live robotic telescopes. Now the chase is on to see who is going to be the first to capture this enormous stellar explosion. Now, before we welcome my first guest, let's take a look at a couple of members' Blaze Star observations that they shared with the community. So an observation is an image that a Slooh member or student captures, and they share it with the rest of the community. Now, have we got, yes, this is Edwin D, right? This is a great little story just from this student starting off in Slooh. And so what he did was he chose the Blaze Star as his first ever target when he joined Slooh, when his school started using Slooh in their studies. He's determined, if Edwin D does not be the first person to capture the Blaze Star when it goes boom, you know, he deserves an award anyway. But we've also got another observation that we're going to share. And this is from Carol Botha. And she shared this capture of the Blaze Star using the same telescope that we were going to use tonight, the 17-inch telescope in the Canary Islands. And let's hop back actually, so we can see there the Blaze Star. Carol's labeled that, but let's hop over again to that Canary all-sky camera if we can. Now, I know that the studio is going to keep a close eye on this. It doesn't look like the clouds are going to part, but who knows? You never know that in astronomy. But anyway, we will have live feeds later if the weather clears. Now, don't forget, students and members can ask us any questions in the Zoom webinar during the Star Party, but let's get underway to learn more about the Blaze Star with our first guest, Slooh's Director of Curriculum, Dr. John Bovair. Welcome, John. How are you?
I'm doing well, Paul. How are you?
I'm very well. I've been looking up today in the prep for this particular Star Party, at all of these observations that members and students have shared of the Blaze star. And I know in the second segment that you're doing, you're going to show us what students can do in our Quest learning activity, because you've created this special Quest learning activity where they can animate kind of before and after images. But we're going to look at that a little bit later. But let's start back at the basics, John. What is the Blaze star?
Oh, going off on what you were saying earlier, it's the Blaze star is a variable star, which is a star that changes its brightness over time. And there's different kinds of variable stars out in the universe. They're not all nova, for example. Some of them are massive stars that are pulsating and getting very large and then getting very small, which causes them to change their brightness. Other stars, there's multiple stars that are orbiting each other right in a way where one star will eclipse the other and cause a variable nature to come forth. But the Blaze Star is a little different since it goes boom every 80 years. When this happens, it's going to be about 2,100 times brighter than it currently is. And as you mentioned, this one is a recurrent nova. And there's a famous astronomer, Robert Burnham Jr. He called this particular system a freak of the heavens because of its recurrent nature and how bright it gets in the sky when it goes nova.
So you telling us, John, that star, that pinpoint of light that Carol Botha has pointed out in this particular image that she captured with the Canary 2 telescope, there's actually two stars there. That's a binary system. Is that what you're
That's
saying?
That's right. That's right. There's actually two stars there. Now, believe it or not, about 75% of the stars that we see in the night sky are actually part of multiple star systems. So that kind of makes the solar system a little unique in that way, where we only have one star. But the Blaze Star system, like you mentioned earlier, is a multiple star system. There's a red giant star orbiting around a white dwarf star. Now, they're not really orbiting around each other. Both of these stars are orbiting around the common center of mass between both of these stars. But usually, when you see the image, like what Carol Botha posted or shared through an observation, we're seeing light dominated from that red giant star. But every 80 years, when the nova happens on the surface of the white dwarf star that's next door, the light from the nova explosion will greatly outshine the entire system. Um, so what's
Wow.
happening here is the white dwarf is gravitationally attracting material from its companion star, and the material forms a disk like we saw in the diagram just a moment ago.
Oh, let's hop back to
And
that. Let's hop back to that to see it. So we've got the white dwarf on the left. We've got the red
mhm,
giant star on the right. And these are two very, very old stars, aren't they?
very old stars. The sun is called a main sequence star because it's burning hydrogen in its core, but these stars are further along in the life cycle of a star like the sun. As you can see, there's a bridge of material coming from the red giant star, kind of swirling around the white dwarf. And if you look kind of close to the white dwarf, you can even see little streams of material coming from the disk onto the white dwarf itself. Now, the white dwarf is like I said, gravitationally attracting the stellar material from the nearby red giant. And over time, that disk gets bigger and bigger and more massive until eventually it reaches a threshold where the material from the disk starts to fall onto the white dwarf. And
Okay.
this is what is causing the explosion.
Just as a digression, is the red dwarf, is that the ultimate fate of our sun?
The white dwarf is the ultimate fate of our sun, yes. And actually our sun will go through a red giant
The
phase
red
too. So
giant
in an
phase does.
interesting way,
Okay.
yeah, red giant phase first, and then it'll turn into a white dwarf. So it's kind of fun that we're seeing, different stages of where our sun is going to be eventually.
Wow. So, oh gosh, that tells us the scale of this thing. I mean, our sun is totally dwarfed by the red giant in the Blaze star system. But you're
Mhm.
saying that at some point, our sun, that tiny little dot, is going to turn into this red giant?
Yeah, it is. It is. And this is the red giant that's in the Blaze star system. Total comparison. So the red giant is 75 times bigger and 650 times more luminous than the sun. But the interesting thing is if we put both of these stars on a scale, they would be actually pretty similar in weight. The sun is the Blaze star, the red giant star that's in the Blaze star system, has a mass of 1.12 solar masses. So it's only just a little bit more massive than the sun is. But because of what's going on in the the internal layers of a red giant star, it causes the star to puff up and become very large. And because it becomes very large like this, it actually loses temperature on the surface. The Blaze star, the red giant star that's in the Blaze star system, is about 2000 Kelvin cooler than the sun. And that's why it's red instead of yellow like the sun is, or a pale yellow like the sun is.
John, if our sun gets that big, thinking about our solar system, we've got the planets Mercury, Venus, and then Earth. Could it get large enough to engulf the inner planets?
It will get that large, yes, to engulf the planets. Certainly Mercury and Venus are going to be engulfed. The question is out whether or not the Earth is going to be engulfed. I've seen some studies saying that it will engulf the Earth. I've seen some that'll say, well, we come very close to the Earth's orbit, but not completely. Either way, the Earth is not going to be inhabitable to us humans
Yeah,
once that
either way,
happens.
it's going to be pretty hot and toasty. Yeah. So, what we've got here then, John, is the white dwarf. What can you tell us about the white dwarf and what's this diagram that we're seeing on the screen?
So this is a two scale comparison between the white dwarf in the Blaze star system and the moon. So the white dwarf is very, very small. Dwarf is an understatement for these types of objects. The white dwarf is only about 0.005 times as big as the sun, so a half of a percent of the sun's size. So instead of using the sun, the moon is a very good representation. It's about twice as big as the moon. So the next time you see the full moon in the sky, which we just had a beautiful one last night, you can kind of mentally multiply the moon by two, and then that's about how big the white dwarf is. Now, what's wild about white dwarfs is the material that they're made out of is not anything like we've seen on Earth. Even though the white dwarf is this small, it's actually more massive than the red dwarf that's nearby. This white dwarf, it has a mass of 1.37 solar masses. So it's wild to me that it could be so small, but yet be heavier than this gigantic star nearby.
Wow. So, this is saying then that that uh, what is it? 1 teaspoon full of white dwarf matter is equivalent to 23 adult, adult, not small, but adult African elephants.
That's right. That's right. These we have to kind of figure out, I thought that African elephants would be better than like any other type of unit, but that's true. And what's going on here is in a typical star, there's a tug of war that's ultimately going on
Mm.
continuously, where you have gravity trying to smash the star into one point, but you also have fusion going on in the centers of stars. The sun is fusing hydrogen into helium. Red giant stars are fusing helium into carbon. And the fusion process generates a whole lot of energy in it, and it helps push against gravity, keeping the star pushed outwards. But for white dwarf stars, this is what's going to happen to the sun. Well, the sun and the red dwarf that's nearby, for that matter, they're not massive enough to start fusing carbon into heavier elements. And so once the cores of those stars become carbon, there's nothing pushing back against gravity. So the star starts to collapse. And white dwarfs are actually um, compact objects because what's happening is gravity is trying to squeeze all of that newly formed carbon together, but the there's no available there's nowhere for the electrons to go anymore around the carbon atoms. And so the electrons generate a what's called an electron degeneracy pressure that holds the star up. And so because all of the carbon atoms are able to get so close to each other, much closer than it can in any environment here on Earth, we get a very dense object. So nothing
Wow.
on Earth has a density comparable to 23 adult African elephants per teaspoon or per 5 milliliters if that's how you roll.
Yeah, I think we need to do this calculation on a whole range of animals, actually. So,
I
I think,
like that.
yeah, I think that that should be a quest. That should be a quest learning activity. Please calculate the mass of a teaspoon of white dwarf matter in different animal kinds. But John, I mean, it's mind-boggling, frankly, to try and get our heads around this. I mean, frankly, even seeing that the size of the white dwarf star is only just slightly bigger than our moon, but contains so much matter. But kind of let's go back. I mean, that kind of hints that this is an incredibly peculiar, exotic animal out there in the universe. So let's go back to the upcoming nova event. I've heard the term supernova way more than I've heard nova. So, what's the connection between the two of these, a supernova event and a nova event, which is what's happening with the Blaze star?
That's a really good question because I've experienced that as well. Always hearing about supernovae, but never
Mm,
anything about novae, or at least very little about novae. And so most supernovae are the result of what's called a core collapse of a massive star at the end of its life. Now, when I say massive stars, I mean stars that are even bigger than red giant stars. Astronomers call them supergiant stars because that they're so creative. I mean, what's bigger than a giant? A supergiant.
super giant.
And And so in those types of explosions, the core of the star collapses on itself and it creates this massive bounce back explosion that is so bright that you can actually point them out in a galaxy where they happen in. So
Yeah.
they become more bright than an entire galaxy. However, novae are a little different. They're massive explosions on the surface of the white dwarf star. So as I was mentioning earlier about the white dwarfs, they attract material from the neighboring red giant and they create a disk around the white dwarf. But once that disk gets massive enough, that material will fall onto the white dwarf surface. Now, because the white dwarf is actually incredibly hot because there's so much energy in that area and gravity's trying to push it all together, but the electron degeneracy pressure is pushing outwards again. That material, which is mostly hydrogen, hits the surface of the white dwarf star and it triggers a thermonuclear explosion. So hydrogen is fusing into helium right on the surface of the star because it's so incredibly hot. And this is what we see when the nova is so bright. Now, what's really interesting about that is I mentioned earlier that the stars are being held up because there's fusion process going on in their cores. And the sun is currently fusing hydrogen into helium. But there's actually a couple of different mechanisms for stars to fuse hydrogen into helium. And the sun is using what's called the proton-proton chain, which you can learn all about in some of Slooh's learning
I've
activities
seen it in
called
the
quests.
quest. Yeah.
But stars that are a little heavier than the sun, that are 1.3 solar masses or larger, they have another mechanism. It's called the CNO cycle, where they use carbon, neon, and oxygen to kind of jumpstart the fusion process. And what's really cool about white dwarf stars is they're basically just a big ball of carbon. In fact, one of my professors he originally came from Kyoto, Japan. His name is Kentaro Nagamine. He told us that white dwarfs are basically carbon stars, and that's always stuck with me afterwards. And it makes sense because they can't fuse anything heavier. So when that material falls onto the white dwarf, it uses the CNO cycle to create this thermonuclear explosion. And what's really cool is when we point telescopes with spectroscopes to novae, that's what we see in the light coming from these novae.
Wow. You were mentioning, John, some of these chemical processes, these nuclear reactions that are going on. It sounds like the stars originally kind of had a load of hydrogen in and maybe a bit of helium, but then they're generating these other elements. Is that right?
That's right. Yes, the supergiant stars are amazing for the universe because they're basically the nuclear furnace where all of the elements from iron and lighter are formed in the centers of those stars. So when the universe, right after the Big Bang, the universe was mostly hydrogen. And so stars are the universe's mechanism to create the rest of the elements on the periodic table. And then
Wow.
the supernovae that happen at the end of a supergiant star's life are responsible for creating the elements from iron all the way up. And so it's amazing. The famous astronomer Carl Sagan said that we are all star stuff, and it's
Star stuff.
literally true.
It is literally true. I mean, so all of that is making sense in my brain. So supernovae mark the end of a massive star, and we're talking about something which is 8 times the mass of our sun, and novae explosions are on white dwarfs. Is that right?
That's right. That's right. Now, there's actually a really cool little wrinkle in this. When I talked about supernovae, I
Okay.
said most supernovae are from the
Oh,
result of core collapse of a supergiant star. But there's another type of supernovae. It's called a type 1a supernovae. And this happens when if there's a white dwarf in the universe that somehow was able to gain mass gain mass to 1.4 solar masses, it's going to the white dwarf will actually collapse and trigger a type 1a supernovae. So I was mentioning that these carbon atoms are pushed together and there's nowhere for the electrons to go. But if that white dwarf makes it to 1.4 solar masses, then that is the threshold to where gravity can finally win in that tug of war and cause the white dwarf to collapse. And when this happens, it generates these type 1a supernovae. And literally all of the matter that's in that white dwarf gets converted into light and other energy like neutrinos. So when you think of Einstein's famous equation E equals mc squared, that m is the mass of the white dwarf, and all of that mass gets converted into energy, and there's nothing left.
wow.
And this system, the white dwarf in this system, is at 1.37 solar masses. There's only 0.03 solar masses it has left to get bigger before it too, boom, goes type 1a supernova.
This is why I love science and astronomy, John. I mean, we still don't fully understand all the mechanisms that are going on, but we're making good inroads to it, aren't we?
We are. And you know, things like these type 1a supernovae are pretty important because distance is a very hard property of any system to measure. And so astronomers have to use this thing called the cosmic distance ladder to get these distance estimates. And these type 1a supernovae are very important for those because, as I mentioned, all of the white dwarf gets converted into energy. And so that means there's a range of known brightnesses, luminosities that these type 1a supernovae peak at. And so if we see them out in the universe, then we know, oh, hey, that's like a 100-watt light bulb at the end of a field. Now that I know that it's a 100-watt light bulb, I can figure out the distance to
The
it.
distance
And we
of it.
call those standard candles.
Okay. And they have been so important, haven't they, since the early 20th century in our understanding of the scale of the universe. But if there are different kinds of supernovae, are there different kinds of novae as well?
There's four different kinds of novae, and you mentioned one of them early on, the special recurrent novae,
Hmm,
which are novae that have two or more eruptions every 80 years or less. But there's
okay.
three other kinds of novae. There's and there's fast novae, slow novae, and very slow novae. And each of
once
these,
once again, it's that real creativity in astronomers' minds, isn't it? What did you say? Slow?
yeah,
Yeah.
slow, fast, and very slow. And but they uh distinguish these different novae based on the novae's light curve, which is a graph that's like what we see here. This is the light curve for the Blaze star system, and it's a graph of the brightness of the system over time. And so fast novae are systems that have a very rapid brightness increase, and then followed by a decline in brightness that goes to about 1/16th of its peak brightness in about 100 days or less. So here we can see that the peak brightness happens at zero and it pretty much goes down almost by like 20, 25-ish days. And so this is a very fast nova. The eruption happens fast and then it goes back to its normal state in less than 100 days. But slow novae have the brightness decline happening over 150 days or more. So they're rather bright, or they stay bright for longer. Not that they're necessarily bright enough for us to see with our naked eyes, like this one will be, spoiler alert. But there's very slow novae, which are very strange because they'll stay at their maximum brightness for about a decade or more before they fade. Um, Another thing that you mentioned earlier is these recurrent novae are very special because we don't really see very many of them. There's only about 10 examples of recurrent novae that we've discovered so far. And while 10 may seem like a lot, back in the late 60s, there was only six known, or seven known,
Wow.
excuse me. So these are quite rare objects to see. However, even though it is rare, it is kind of related to how long we've been looking into the sky, even and especially with the technology and equipment that we have today. Astronomers theorize that most, if not all, novae actually are recurring novae, but they could have
Okay.
timescales ranging from 1,000 years to 100,000 years. So that means we'd have to be watching that system for, 100,000 years before we can see it happen again.
Okay.
Um, so yeah, so that's something that we could consider. Another thing too is how how heavy the white dwarf is also kind of determines the interval between the different nova events. The more massive the white dwarf is, the more gravity it has to pull its material from its neighbor, which decreases the interval between the nova events.
There
So
must be so many factors there. It's about the red giant as well, how big, how close, the proximity of them. And this is with such a small sample of only 10 known recurrent novae. Our sample is really small, so it's pretty difficult, but it also makes events like this so important when so many people, including Slooh members, are pointing our telescopes towards this because that's how that light curve is generated, John. I don't know if you want to explain just before we go on, to how we forecast
yeah,
when the blaze star is going to go boom. Just explain this diagram of what we're looking at because we'll talk to Michelle Park later because her study was about variable stars as well. And I suspect that this is exactly the kind of thing that she was generating. Light curves. What is a light curve? We can kind of see the two axes there, but could you explain it for us?
absolutely. So this is the brightness of the Blaze star system. The y-axis is the brightness. Now, astronomers use what's called the magnitude system
Right.
for brightness. And so in that system, the lower the number, the brighter the object is. So I put in the bright and dims in the axis here for us to
Yeah.
remember that. And then along the x-axis is the number of days since the peak of the eruption. And so what's really cool is when this system first erupted, it happened in 1866, and they were calculating and making this light curve after it happened. And this is what we see as a solid line on this plot here. So this is the 1866 explosion.
Right.
Now, when the blaze star went erupted again 80 years later, it's what we got as this dashed light curve. And so what's
Right.
really cool then is you can put both of these on top of each other and you can see that they're basically following the same exact patterns as we saw before. So this is kind of telling us that this is the same event that we're seeing here in 1946 as what happened back in 1866.
So this is how we're able to forecast that the blaze star is very close to going boom because we have already measured that interval between these recurrent novae events. Is that right?
That's right. Now, what's different with this is the before the 1866 eruption, we didn't really know that that star was going to go nova. So we didn't have data for what was happening with the system before eruption. But because the star went nova in 1866, astronomers have been continuously looking at the star for any evidence of any changes. And so if we go to the next slide here, this is showing what was happening in the couple of years before the eruption happened. And so
Okay.
this is using data from the AAVSO, which is the American Associates of Variable Star Observers. This organization houses data for variable stars, which is actually really cool because Slooh members today have already been submitting measurements for
Mm.
to the AAVSO for over 20 years now. So it's a really fun thing. So here, if you look maybe about a half a year, a little more than half a year before the eruption, there was a dip in the brightness of the system. And so that's called the pre-eruption dip. Do you
Okay.
notice, can you see that dip there in the
Yeah.
light curve?
So what's going on there, John?
So what's going on is at this point in the stage of the nova, the disk is getting very full of material from its neighboring star. And because it's
Okay.
getting very full, it's able to more effectively block light from the system. And so we get this kind of dip in the light because there's so much stuff and it's ready to just fall onto that white dwarf and start the nova process.
I love that we can infer this just by observations of the light being emitted from that star system. Could we go back to that diagram of the white dwarf and the red giant and the accretion disk? Um, let's take a quick look back at that, John. So you're saying that in the pre-nova event, when the star system goes boom, that accretion disk of the white dwarf attracting all of that matter from the red giant gets so thick it actually dims down the light that's coming from the entire star system.
That's that according to research, that seems to be the likely scenario what's going on. Yes.
Wow, it's incredible that we can see that in that data.
I know I can't believe it either. And what's even more mind-blowing about this is that we've already seen the pre-eruption dip in the light curve for the Blaze star. See, our original estimate for the Blaze star going nova was around December of this year. But
Okay.
in mid 2023, we saw this pre-eruption dip, and that allowed astronomers to improve the anticipated eruption date to sometime between January and in August. So it could happen any day now. It probably even add September in there too. So it could literally happen any day now. So
But
if you're a student that's watching this, you could be the one to see it and capture it for the first time.
exactly, who is going to be the first? There are so many people around the globe monitoring this star every night, but students using Slooh have got a big advantage. With the opening of the new Australian observatory, we've now got 24-hour live astronomy. So whether or not you're using the Chile telescopes, the Canary Islands telescopes, or the Australian telescopes, it's visible in all of those. So you've kind of got three bites of the cherry in one go. But John, we've seen some marvelous observations that students have already shared of the Blaze star, monitoring it every night. What are they actually going to see when it goes boom?
So when we look at the Blaze Star and Slooh's telescopes, what's great about those observations is it kind of gave you a little a way to figure out which one of those dots is the Blaze Star. But when it happens, the system is going to get incredibly bright. It's going to be um, akin to some of the brighter stars that we've seen in Slooh's telescopes, which is actually I'm going to show a mock-up of what the
Oh,
Blaze Star can potentially look like
nice.
in
In
the
the
next segment
quest.
when we go through the quest.
Okay, that'll be fun. So, will can people see the Blaze star with their naked eye without a telescope at the moment? And will they be able to see it naked eye when it goes boom?
It's a fantastic question. And so before the nova, no, we're not able to see it in the sky, but we can with Slooh's telescopes. It's very no, easily you can easily pick it out there. But once the nova occurs, yes, we will absolutely be able to see it in the sky. And I can give you and I can give you a little
Hmm.
constellation hop and how to find it. But what's interesting though is this is where the term nova comes from. Nova is Latin for new, and so
Mm,
a nova is a new star that we see in the sky. So before the system is nova, we can't see anything. But when it is nova, it looks like all of a sudden a new star appeared in the sky. And so if we want to look for it, it's going to be about the same brightness as Polaris, the North Star, or the star Hamal in Aries, or the brightest star in the Hydra constellation, Alphard. And as we saw on the light curve just a moment ago, it's only going to remain that brightness for probably about like 2 or 3 weeks before it goes back to its original brightness. So the Blaze star is in the Corona Borealis constellation, which you mentioned earlier. Its scientific name is T Corona Borealis, which stands for the Northern Crown. Now, the best way that I have found to figure out where to look in the sky with the naked eye is this following. So and then I'm going to take a very urban astronomy approach to this because there's no way that you can see all of these stars if you're in
mm,
the middle of a city, where I'm at. But the Big Dipper is an asterism that's a smaller part of the Ursa Major constellation, and the handle of the Big Dipper has a little kink in it, and that star is named Mizar or Mizar, depending on how you want to pronounce it. And there's this old astronomy saying that I love teaching students, and so everybody here gets to get it now. The best way to find the star Arcturus in Bootes is to take that arc of the Big Dipper and it arcs to Arcturus. So
yep.
Arcturus. And so once you get down to Arcturus, it's a very beautiful orangey reddish star. You'll want to look a little bit above it. And when I look a little bit above it, I can see this if you follow along the left constellation line of Bootes, I can see that first star there. But once I see that, the only thing I can see that's to the right of that star is the brightest star in the Corona Borealis constellation. It's called Alphica. And maybe one pinky width from Alphica is about where the Blaze star is. So
Okay.
what would be what would be very good if is you want to start kind of practicing looking in that direction of the sky when there's clear skies where you're at. That way, once the Blaze star happens, you can be super savvy with all of your friends and walk outside and say, "Oh, it's right there. That's where the nova is."
And Corona Borealis is, you need to have pretty good skies for that. You need to have pretty dark skies to see that constellation. But it is such a distinct curve shape, as we can see there in the diagram. How bright is the blaze star going to be in comparison to the other stars in that constellation, John?
It's going to be a little bit brighter than Alpheica. So Alpheica,
Okay.
if I remember right, is 2.2 magnitude, and the Blaze star system is going to be around 2 magnitude. So it's going to be
I,
just a little tiny bit brighter.
I think it's going to be quite a distinctive distortion of that constellation if everybody gets used to seeing the constellation as it is now. And we're going to talk about that later because so much of astronomy is about comparing how something is now and how it's changed. So I know we're going to look at that later. John, anything more about the Blaze Star before we move on?
One more thing. So I mentioned that the Blaze star sometime in the future is going to go type 1a supernova. And when that happens, because of how close it is, about 3,000 light years, and we know that when type 1a supernovae happen, they're about 10 billion times brighter than the sun, and it'll be that bright for a month. The Blaze star system will be about the same brightness as a quarter phase, so first quarter or last quarter moon phase. So it'll be bright enough to see during the day once that goes type 1a supernova. I think that's kind of
Wow.
cool.
Wow. Not sure I'm going to see that in my lifetime. Frankly, I'd be
Nor mine.
extremely lucky to see the Blaze Star go in another 80 years' time. John, thank you so much for explaining all of that. Viewers and students must not miss our next segment where you're going to be showing them a really brilliant tool. I think it's my favorite tool in our Quest learning activity system, where we're going to blink compare two images. So you're going to show us that later, aren't you?
But yes, I am. I am. So stay tuned for that.
Definitely. Thank you very much for now, John. We'll see you a little bit later. Now then, let's get on. I would like to welcome a very special guest to the Star Party now, longtime Slooh member and now Stanford University student who has been enjoying, slightly jealous here, an internship at the Jet Propulsion Laboratory this summer. Michelle Park. Welcome to the show, Michelle. How are
Hi,
you?
I'm so glad to be here. I mean, it's been quite some time since my last star party, and what better occasion than the Blaze Star itself?
Exactly. Well, we've missed you, and you've got a fascinating story. And frankly, it's truly inspirational for other students to see how hard work and dedication has already put you on a kind of career rocket trajectory, literally, because you've been working at JPL this summer. But let's go back to the beginning because I'm always fascinated by our kind of individual personal origin stories. How did you first become interested in astronomy and science? What do you put that down to?
I think it definitely has to be Neil deGrasse Tyson's Cosmos show. So
Oh, right.
growing up, I would literally come back from school and watch it every night when the new episodes came out. And it was really fascinating in that there was really a lot of world building and storytelling about what's out there in the universe. And as a
Mm,
young kid, I was really interested in that. And as I continued throughout middle school and high school, I just felt my interest in space and eventually even physics grow more and more. So that's sort of how I came to get interested into space. I really think that every student or everybody has a natural inkling as to what's out there. Space really is a universal unifier in our
yeah,
passion for science. And so, regardless of whether you're doing astrophotography for fun or if that sort of leads you down the astronomy path, I really think that astrophotography and just hearing about what's out there in the universe sparks joy. And that's exactly what it
yeah.
did for me.
It's the awe and wonder, and I think especially the Cosmos series, both Neil deGrasse Tyson, but I watched the original with Carl Sagan. Um, it's the storytelling. It gives us our a sense of place in this vast universe. But coming kind of back down to earth, how did you come across Slooh? Because you didn't join Slooh as a member of a school that were using Slooh. You joined as an individual. So How did you come across Slooh and when did you first join?
I believe I first joined in like 2017, 2018. My encounter with Slooh was entirely coincidental.
Okay.
Back then, I was like a high school student, and I really wanted to do a research project on variable stars. The issue is, though, that I come from Ohio and the weather is not great. There's a lot of light pollution, and I knew I couldn't do this on my own. So I was Googling some online resources that could potentially like help me photograph the night sky. And what I found was a lot of very expensive
Mm,
subscriptions, a lot where I felt like I didn't have enough control of what I could photograph. And then I encountered Slooh. And what was really impressive about it was I could put in the coordinates to any object that I would want. But I also felt like I had a lot more freedom in when the photos would be taken and sort of what format. Because I could get them as a normal image or as a FITS file, which is this like special astronomy file with like extra data and information. So
yeah.
that was sort of how I started. And yeah, no, that's how my research project with variable stars and Slooh began.
So, how did you decide on the topic of study for your self-directed study?
Well, I really have been interested in variable stars just because, like John mentioned, they're used as sort of like cosmic meter sticks to measure distances, similar
Mm.
to like the supernovae. Um, but I also felt like it was something that was feasible for me to take photos of and also really cool to show other people. I think it's one thing to show an image of the night sky and be like, hey, here's a star, but another thing to be like, hey, I tracked this star for months and I saw that its brightness changed over time. And so that was what really drew me to that topic.
So you were generating, I don't know if we can go back to the light curve of the blaze star. You were generating light curves over a period of time of the particular type of variable star that you were monitoring, were you?
Mhm. Yes, exactly. So I was looking at RR Lyrays or RR Lyrays. Um, and they're a specific type of variable star, and they have much shorter periods. So here, it's across many years. My photographs only went through a few months, and within that time, I was able to see the up and down motion of the brightness changing over time just by taking a ton of Slooh images.
It must have been so exciting the moment that you started seeing a curve develop on your light curves. Were you? It must have been thrilling.
Yeah, it was many years ago, but I still remember the day that I saw that appear on my computer screen. I think I like jumped around with joy. It was really a profound moment because it meant that all these images that I took for months led to a light curve and really showing that I could take photos of these variable stars.
And you collected all of this data, and I, it only you kind of did this really stealthily. I've never told you this before, but I used to look at the schedule of the telescopes, the Slooh telescopes, and I started seeing your name appearing with these same missions over and over again. I thought, what on earth is that member up to? But this, your self-directed study and research, you turned it into a scientific paper, which was published, wasn't it?
Yes, that's correct. So it was published in the Journal of Emerging Investigators, which is designed for high school students to sort of get practice with scientific writing, publishing, and the peer review process. And that was a really great process. And yeah, no, I remember I was a little stealthy at the start. At first, I guess I was just collecting images of my favorite nebulae, and then I took it to
Hmm.
the project, but I was also really excited when all the publication came out, and I was really excited to share it with all of Slooh. And it was really just the culmination of months of effort.
You have inspired so many people. Can you just remind us how old you were when you published this scientific paper?
I think I must have been like 16 or 17. I remember it was maybe my sophomore or junior year of high school. Um, So yeah.
Do you get how special that is, Michelle?
I mean, it still amazes me to this day. I mean, none of this would have been possible without Slooh and just the amazing community here. I
You're,
remember I lo asked a lot of questions on the community page,
yeah.
um, and just got so much great support. There is a variable star community, or at least people taking photos of variable stars with Slooh, and they have been an immense resource for me when I was starting out.
Well, I'm glad to hear that because it's the best kept secret in the world, the Slooh community and how supportive they are. And it's not just variable stars that members are monitoring, but it's comets and near-Earth asteroids because there's so much, isn't there, that we can learn from these light curves. I mentioned to John a little bit earlier, so much of astronomical discovery is about spotting the difference. If you're good at spotting the difference, then frankly, an astronomical discovery is coming your way.
Yeah, no, exactly. I mean, that's how they discovered like Pluto, right? Because the guy who discovered Pluto was really just spending all night comparing images back and forth of these tiny patches of the night sky. Um, and I guess that's how really cool discoveries are made.
Hi, Tom Bauer is one of my heroes of astronomy. I think he started off as a farm boy and squeezed his way into the Lowell Observatory in Arizona and managed to kind of step up the ladder. But he was taking images on these huge glass plates, about 20 inches square. And it took hours and hours of him staring through the telescope to guide on the stars to make sure that all the stars were pinpoint. But now, I love showing this. This is one of the astronomical cameras that you were using. This particular one, Michelle, did you
Wow.
know this is the one that you were using to create your paper? It's no longer in service, but this is it. This is a CCD camera. You were capturing objects within 50 seconds using this camera and telescope that it took Clyde Tombaugh 3 hours of meticulous observation to collect. And this kind of technology is in the hands of students of 15 and 16 and younger to perform real science. But moving on in your fascinating story, and honestly, you're so humble, you don't get how inspiring your story is. And if anybody wants to know more, there is a case study on Slooh's website about Michelle, which has recently been updated. So stepping on, you must have been thrilled to be accepted into Stanford University. Tell us how that felt. Can you remember?
I mean, I like that was really just a life-changing moment. I remember I was screaming and jumping and running around the house. Um, yeah, no, it was very, very amazing. And honestly, my journey at Stanford has it's just gotten better and better. I mean, um, there is such a strong, amazing, inspiring astrophysics and physics community here, ranging from professors to fellow students
Mm.
to even having our own observatory at the university itself. So I mean, I was incredibly excited when I got in, but I think I'm even more excited just having access to so many amazing resources and an amazing, kind community.
And being immersed in that environment with your peer group as well. So many of us who are kind of, excuse me if you're not, but I'm a little bit of a geek. I kind of stood out in school a little bit. I was the only person who was really into science and technology and stuff like that. But suddenly you land up in this environment, and I kind of looked around and said, these are my people. I don't know if you felt the same, have you?
Yeah, no, I mean, exactly. When I first came to Stanford, at first, I was like, wow, there's people from all sorts of different places, backgrounds, identities, perspectives. How is this going to work? And then I remember my first day of physics class, I was just surrounded by all of these bright minds and people asking all of these amazing questions. And I really thought to myself, like, I'm going to learn and grow here. And I
Mm.
think you really become the people you surround yourself
Yeah.
with. And I would not be more grateful to surround myself with this type of community.
So it's not the end of the story because you've had, I think it would be fair to say, a pretty good summer, haven't you? You got an internship at the Jet Propulsion Laboratory. What happened there? How did you get that? Were you on the phone? Were you badgering people? Let me in. I want an internship there. You were. I can see it.
No, actually, the story is really interesting. So I know this professor, Professor Dusty Schroeder. He's actually the second author on the paper I published on the Slooh telescopes. He has been a longtime mentor of mine. We first met when I was in middle school. I did not expect him to reply to my random email, but here we are, and he has been an amazing mentor. He's a professor at Stanford, and I have been part of his group. And last summer, he took me to a conference on radar and radioglaciology. So this was
Mhm.
totally new ground for me. And when I went to the conference, I met another JPL scientist there, Gregor. Um, and we were just chatting about sort of the research I was doing and so forth. And the next summer, I was thinking that it would be so great to explore a different side of physics, something
Mhm.
that's a little bit more engineering, but still related to space in a really cool way. And Dusty, my longtime mentor, suggested, how about JPL? And that's sort of how it started. And Gregor, who I met at the conference, was more than happy to get me on a project. And it just happened to be Europa Clipper, which is a really, really exciting spacecraft that's actually going to launch, I believe, in a few months. So
Yeah,
happy
October
opportunity.
4th, is that maybe?
Sorry, could you repeat that?
I think it's October 4th because we're going to be
Oh,
covering the live launch of that. So, and we've already invited you to that star party.
yeah, I mean, I would be great. It would be great for me to be there.
So
But yeah,
you're
no,
part of
long.
this mission. You're part of this mission, which is so exciting. I mean, this potentially, is going to investigate and observe one of the places where we think life might exist off Earth, isn't it?
Yeah, that's correct. I think Europa has been a really active area of research because we've really sent only a few spacecraft there in passing on their
Mm,
way to other planets or to the interstellar, like outside of the solar system. And what they've realized is that Europa has three key features. It has heat, which is generated from its immense gravitational pull from Jupiter. It
mm.
has a liquid ocean underneath its surface, which is always good news. And it might actually have favorable chemical conditions, which we've detected from plumes that are emerging out of Europa. Now, a lot of these we need to take a closer look, which is why we're sending Europa Clipper to investigate sort of all three of these properties. And if all these three properties come together, I mean, that's basically a signature for habitable conditions to emerge. So that's really, really exciting. Sort of
It
being a
is.
part of that mission, at
It
least
is.
tangentially as an intern.
No, I think that's pretty cool in whatever aspect you're involved in a project like that, frankly. And, you were talking about favorable conditions for life, or at least a few of the ingredients where life can live. What we've seen on Earth is that life has a way of existing under incredibly extreme environments, whether or not that's volcanic plumes with no sunlight on the seabed, or acidic pools in Yellowstone Park, or at high altitude in the atmosphere, even. Life has a way. So it's going to be a fascinating project. And what a brilliant thing for you to have your name on that. So, Michelle, before we let you go, you've mentioned your mentor, and I always think that, a single educator for some of us, a mentor, somebody that we meet in our life can set us off on our career paths. For me, it was my science teacher when I was 12 years old. He only taught me for 6 months, but he got me, and he just nurtured my interest in science and technology. It sounds like you've had the benefit of your mentor. What advice would you give to students watching who want to forge a career in astrophysics or maybe the new space industries?
I'd say definitely just this might be cliche, but stay curious.
Mm,
Um, I think also like Paul, like you mentioned, having a mentor is very important. I think a great place to start is honestly the Slooh community. When I was starting out with my project back in high school, the Slooh community was such an immense help. And along those lines, another piece of advice I give is don't hesitate to ask questions.
Yeah,
People love when you ask questions, and it also is a benefit to the person explaining because they help learn something new, but also to you because you're also learning something new in the process. So just being able to ask questions freely and yeah, stay curious.
I think that is fabulous advice. Michelle, thank you so much for joining us for today's event. We are going to see you back when the Blaze Star goes boom, which could be tonight. Who knows? The forecast can be wrong, but it's likely to be at some point in September. And I'll tell you, we were thrilled. We were jumping up and down around the house when we heard you got into Stanford, and we look forward to following your continued progress on what is going to be undoubtedly an outstanding career. You really are inspirational. So thank you for sharing your story with us tonight.
Oh, thank you so much for the kind words. I mean, that is so meaningful to me,
Well,
and
it's
I'm just
true.
so thankful for this Slooh community for just always being there. And yeah, glad to be back. So excited for the next star party and
Yeah.
to see the Blaze Star explode.
So be on high alert. Short notice it's going to be because as soon as the first observation comes in, that bang, it's gone boom. We are going live that same night. So maybe schedule out, I don't know, 2100 UTC until 2200 UTC, maybe for the next 6 weeks.
All right, sounds good.
Thank you, Michelle. Thank you so much for joining us and sharing your story again. So,
All right, thank
wow,
you.
it really is truly inspirational. But the community support as well that is there and exists in the Slooh community is not talked about enough, frankly. But anyway, we are running over time because it's been such an exciting show. I would love to go back actually to see some of the observations that Slooh members have already made. If we can go back actually to the all sky camera in the Canary Islands, I'm just confusing the studio now. Let's go back. Let's have a look at the Canary Islands all sky camera, see if the weather is still pretty poor. So it'll be there somewhere. Um, there you go. Oh dear, look, it's still looking white and overcast. That's the domes there on the left. The one closest to us is housing the telescope that we were going to use tonight, the Canary 2 17-inch telescope. The other dome there with the big black line going over, that's where the shutters open. That houses the half-meter telescope in there. We've got a half-meter telescope in in Australia as well. But anyway, we are running over time, so we're going to keep this short. But I am delighted to welcome back Slooh's Director of Curriculum, Dr. John Bovet, to learn about our learning activities. And those are called quests. And one particular quest learning activity about the Blaze Star. Welcome back, John.
Thank you so much, Paul. Glad to be back to talk about the quest,
I
the
know.
Blaze
So
Star.
we need to keep this reasonably brief because I've had such a lot of fun. I'm sorry, a bit indulgent, talking about the Blaze Star and learning about them from you and what novas are and what supernovae are and the different types and stuff like that. But students can use this quest to learn about all of those things. But for those viewers who are new to Slooh, can you tell us what quests are?
Yes, definitely. So quests are the cornerstone of our cosmic classroom that we have here at Slooh. They're basically our learning materials for students to embark on using Slooh's telescopes to learn so many different things about science and other related topics.
Oh yeah, we're going to go and
And
see the
what
quest, I think. Oh, let's go to all quests and search for Blaze. Is it published yet, John? It is, isn't it?
it is published. So if the studio can click on quests and go to Blaze.
All quests
Hey,
and then do a
John, do you
search.
want to just take over and you can do a demo?
It
Oh,
says the host isn't allowing multiple presenter sharing. So as soon as you
Got
stop
you.
sharing, I will
There
take
we go.
over.
Go ahead.
Thank you.
thank you, Gretchen.
Yes, thank you so much, Gretchen. All right, so here is the all quest page. And so we have over 70 quests for educators to assign to their students and for students to embark on. One of them is even the Clyde Tombaugh one where you can uh, discover Pluto in the way that Michelle was talking about just a moment
Mm.
ago, and you too, Paul. What's really cool about Slooh's Quest is that students create they create posters using their images from the telescope. So this is one that goes over the life cycle of a star like the sun. So students can learn about the sun being a main sequence star, turning into a red giant, and ultimately turning into a white dwarf.
So, John, all of
Um,
those
but
images there, students captured with the Slooh telescopes to use in their quest. Is that right?
that's right. That's right.
Brilliant.
Yeah, students have a list of objects that they can capture for each of these different squares on their poster. They schedule the missions themselves. They look at the weather forecast. They look at where the objects are. And then after they gather all of their data, they actually work with those images throughout the quest. So it's a really personalized experience, a personalized quest through space. Then when they get to the poster, they're able to edit the images, crop them, zoom in on them, and then all of the text that's on here is text that students answer, or stu
Okay.
text from the quest that students answer themselves. So it's pretty cool. Um,
You mentioned you mentioned standards earlier, John. What standards are our quests aligned with then?
It's a good question. There's so many different standards out there. All of our quests are aligned to NGSS, which is the next generation science standards. They're aligned to Common Core, and we even align our quests to some of the individual state standards like Texas, Georgia, Alabama, and more are coming soon. Not only that, but we've also aligned these quests to popular astronomy textbooks like the OpenStax second edition textbook and the Cosmic Perspective ninth edition textbook. And again, more textbook alignments are also coming soon.
So, John, come on, I can't. You got me on tenterhooks. Can you please show us
All right,
the
here.
Blaze Star quest? Come on, there it is.
So once you get to all quests, just type in Blaze. There it is. There it is. And so this quest is a two-part quest. So you can read a little bit about the quest, and quest is broken up into different steps, and each step has various panels in it. So step one of the quest is all about what a variable star is, what the blaze star is, goes over the who, what, when, wheres, and whys for the system. And I will say for educators who are listening right now, there's actually information in the quest that we didn't cover in the star party, and there's information in the star party that we didn't cover in the quest. And so this way we actually put links to the star parties so that students can make sure to enjoy the star parties while they're embarking on the quest. But we even have some images on the next step, which is our Nove 101 information about the properties, which is some images that we saw here tonight. There's even other
It's the
images like
elephants.
what would
Yes.
happen. Yeah. And then we even have some images of what would happen if we place the Blaze star right into the solar system. How would the star look like compared to the sun, this little circle
Okay.
here? Or how would the Blaze star's white dwarf look
Wow.
compared to the Mercury, Venus, and Earth? And where would it be in the orbit? So there's a lot of fun things that students learn here. And we also go over the process of a nova, which is something we kind of covered today, but we
Mm.
didn't really go into detail. But the each stage and what happens in a nova. So that's a really fun thing.
John, there's a huge amount of information
When
for the student within the quest, but there might be some science teachers out there who their astronomy, they don't know a huge amount about astronomy. Each quest has its own teacher resources as well. We don't need to show them, but they have teacher resources which include sample answers to questions and what really they should be looking for in assessing their students' work in the quest.
That's right. And not only that, but we also give suggestions of how you can prepare your class for the quest before you do the quest together, some activities to do during class time. If there's a student that gets ahead of everybody else, we
Mm.
have some ideas in there. And we even have some ideas for extending the learning after all of the students get done with the quest. So those are, and of course, like you said, the answer keys are very important, especially for the ones that like are open-ended questions. We even provide sample answers for those as well to give you an idea of what your students should be answering.
So, John, I can see a little bit here saying insert your data. So students in this quest are going to capture images both before the blaze star goes boom and after. Is that correct?
That's correct. That's correct. So if you're listening to this now, because we were clouded out tonight, make sure you schedule some missions now so that you can have your reference images. Because once the star goes boom, you're not going to have a chance to get your reference image now. So, and then what you'll want to do is you'll actually want to schedule missions across all of Slooh's telescope networks because when you're doing these image comparisons, like I'm about to show, it's important to make sure that both of your images are from the same
Yeah.
telescope so that they're the same field of view size. And so what you'll be able to do here, and actually even before the system goes nova, you can use this to just try and see if for yourself if you can watch the catching of the brightness of the system. So let me show you
Yeah.
what I mean. So here, this is our data collection spot. And I already put in, this is my reference frame image. This is coming from Slooh's Canary 1/2 meter telescope. And I can already see that um I can already see that the blaze star hasn't gone blaze yet. And one thing that you'll be able to see, I know that this one's the blaze star system. And the reason why I can tell that is because I always notice this square that's right next to the blaze star. And so these four stars and the blaze star make like this little house in the sky. So it's important to make your own
Excellent.
little asterisms when you're watching
Yeah.
these images. So that's where the blaze star is, and I mocked up what the blaze star could look like based on the magnitude, and so I put that image into frame two. So let me show you what you're going to be able to do. You scroll down a little bit, you can check to see if the blaze star went boom. And if you've never used Slooh's animation tool, there's a really awesome primer that Paul recorded. He'll give you all of the details and skills that you need, but you get to see this. This is the animation module. And so what we need to do is right now we can actually see two images. Let me just click on frame one. So here's the reference frame. When I click on frame two, it's going to put the frame two, smack it right on top of the frame one. But the images aren't lined up yet. And so what you'll have to do is you'll have to use, and when I say you, I mean you as students are going to have to use these arrows to line the images up. Now, I was already zoomed in a little bit. This is usually what you would see. So you see the full image from the telescope, and then the second image just kind of right on top. And you'll want to use these zoom controls to zoom in on your image. And you can already see once you do that, like, okay, here's these two stars, and here's those same two stars. They're just not lined up. And so using the X and Y arrow keys, we can line up these stars. Like, okay, well, maybe this is pretty good. Let's go down a little bit.
It's
And
such a powerful tool. I love it.
boom. And so here is a pretty good spot of having both of the stars. It's such an amazing tool. And if you noticed, the stars were kind of dim, but as soon as you get the images right on top of each other,
Yeah.
well, the stars kind of pop out. Another thing you can do is you can click back on frame one and then back to frame two, and it kind of like if you see the stars moving around a little bit, you know that you might need to fine tune a little bit. But I aligned these before the show, so I knew exactly what the X and Y coordinates needed to be. So once I zoom back out, we can get a preview of the animation by hitting play. And so here, that's kind of what we're going to see when the star goes boom. Now, when the nova happens, it's not going to be this color. I looked up the colors of novae that we've seen thus far, and it should be kind of like a whitish bluish color instead of this
Okay.
orangey color. But I had to find something that was about the same brightness to do this animation.
I mean,
But once you're
it's
happy,
going to be fairly obvious from this mock-up, John, and I don't think you're going to be far off there. This is going to be really obvious when the blaze star goes boom, isn't it?
it is. It's going to be immediately obvious. And once you're done, you can hit finish, and then it will stitch the animation together into a GIF file, which you'll be able to download, share on social media. If you share it on there, make sure you use Slooh's
Yeah.
hashtag share Slooh, and tag us too. We'd love to see it. But if you want to start doing some Nova monitoring, then you can take any two Blaze Star images,
Yeah.
line them up and see if you see it. But like you said, Paul, it's going to be pretty obvious once the star actually goes nova.
But also, I think students, if we think back to that light curve that you were showing us earlier, they can continue monitoring the blaze star after it's gone nova and actually add to their animation to see it gradually dimming again. Using animations, John, is such a powerful technique in astronomers. Astronomers call it blink comparison. And we can see why. I mean, it's just such a good demonstration. What kind of astronomical discoveries can be made using a similar technique as this?
So a couple of things that we've already mentioned together tonight, of course, monitoring nova and seeing nova events, discovering dwarf planets and small asteroids that are in the solar system. We can do that by comparing images, but other things too, like looking for supernovae in other galaxies, since the supernovae outshine the host galaxy they're in. Blink comparisons are a perfect way to see them.
Mm.
There are other things that astronomers use. There's a detection technique for exoplanets called the transit method, which is basically what astronomers are doing here. They're seeing if they see a dip in the light curve because one planet is passing in front of the star. And comets are another great way
Yeah.
for the blink comparison method, recovering them from coming around the sun or just their initial discoveries.
Emmanuel Conseil
And
was,
like as
sorry, John, we haven't mentioned it yet, but Emmanuel Conseil, who was a long-time Slooh member, he's unfortunately not very well now, but he discovered many novae with the Slooh telescopes, and he confirmed countless supernovae as well. I'm just seeing in chat, Jenny is saying she's already captured some reference images of the blaze star on multiple telescopes. So Jenny is well and truly prepared with her reference images. I'm going to capture some more actually, because I know it's a featured object actually, and we're going to leave that as the featured object until it goes boom. John, thank you so much for sharing Slooh's Quest. I do love the animation module. It's so powerful. Is there anything else you would like to mention about the Blaze Star before we wrap up the star party?
I want to piggyback on what you were just saying about how students, after the star goes nova, continue capturing images because of the system, because Slooh has launched a new quest called the Animation Quest,
Oh,
where you'll
yeah.
be able to take 38 images and turn the data into a time series animation. So what would be really cool to see is you get your reference image, you get the blaze star image, but then continue capturing images and actually make a little animation of the system returning back to its original brightness. So that's my challenge for any students that are listening. I want to see that animation posted as an observation sometime.
Excellent. I'm going to
Um,
take out that challenge as well, though, John.
awesome. Me too. And the only other thing I want to say is usually when we think about once in a lifetime astronomy events, I think
Mm.
Halley's Comet is usually the one that people talk about. But
Yeah.
this is just on the same level. Halley's Comet comes around every 76 years. This star goes nova every 80 years. So it truly is once in a lifetime.
Carol Botha is posting in chat saying, "This is so exciting. I've observed the recurring nova RS of Fukai on Slooh and followed up until it faded away completely. So
That's awesome.
that's a fitting end. John, thank you so much for joining us this evening, stepping us through this quest. Please make sure you're not on holiday when the blaze star goes boom, otherwise you will be recalled. There's no excuses for missing the boom star party. So thank you for joining us, John.
Sounds great. Thank you so much for having me on, Paul.
Well, it is time to end the star party. Apologies for overrunning. We can see some observations that students have shared of the blaze star. You've seen John's simulation of what it's going to look like. I didn't really realize until I saw John's simulation about just how obvious it is going to be. So make sure you check your blaze star images every morning. I'd like to thank our two special guests, Dr. John Beauvais and Michelle Park, sharing her amazing story. Make sure you capture the blaze star every night. Who knows, you may be the first person to witness it go boom. And do start the quest now so that you can capture those before and after images. And when it does finally blow its top, we will have a special star party to celebrate. So keep your eyes peeled on Slooh's website and our social media where we'll announce that. There are some other events planned too, though. We have International Observe the Moon Night on Saturday, September 14th. That's always exciting. We've got some members who are kind of crowdsourcing live video of the moon from several locations. So that's going to be a good one. And we've also got, this is a fascinating event. It's a whole collection of different things happening all on the same night. It's a harvest moon. It's also a supermoon. It's also a partial lunar eclipse, and that's on Tuesday, September 17th. That one should not be missed. I'll tell you, that's going to be a great one. It's the largest supermoon of 2024, and it is going to be made extra special because it's going to be partially eclipsed as the moon enters Earth's shadow. Something a little bit earlier than that, though. Saturn is going to be passing behind the moon tomorrow night. That's Tuesday, August 20th. It's already Tuesday for me here, nearly, in an event known as an occultation. And we've set up some special missions using the Canary 2 telescopes to capture the ringed gas giant slip behind the moon. If you've never seen an occultation, it's a remarkable thing to see an object so close to us like the moon, but to see this distant tiny planet. You can barely see its rings at the moment because they kind of edge onto us, but to see that just slip behind the moon and then slip out at the end. We have no idea how those missions are going to turn out, but it's a bit of an experiment. So join the live telescope feeds tomorrow, Tuesday, August 20th, to see Saturn slip behind the moon. But that's it for now. Until next time, thank you to all of our guests. Thank you for Gretchen for holding the studio and keeping us running tonight. Till next time, clear skies, everyone.